I'm dreaming of a space weather at time of solar minimum. May your sun be active and bright, and may all your sunspots be black. 193 angstrom solar disk. Not a lot going on. Tiny active region or two, coronal hole or two rotating through. Let's look at some other views. I don't know why it's loading so slow. SDO, your servers are jacked. Anyway, you can see some filamentary activity around the southwestern limb area, northeastern limb area also. And let's just move on because we don't have all day for this. And the 171 angstroms view. Yep, I don't know what's wrong with these animations today, but they're not loading right. It says it's loaded. There it is, not playing. Moving on to something with the data we're looking for, as we have 21 tabs open. Here are your magnetic lines at 335 angstroms. See the coronal hole regions are to the south. And the North Pole is actually dominated by pretty dense fields, especially in this area. Looking at earthquakes over the last 8 hours. Dominica gets a 3.4. Let's see. Japan, that's only one quake, 4.9. Looks like an uptick in Alaska. Let's take a look at the swarm in that area. Oh, that's the northern part, okay. Interesting. One of the larger quakes we've seen in that region. So 2 of them there, and they are different quakes, it looks like, although they were only 3 seconds apart. That could be the same quake. 4.2 in Peru. Peru should stay on alert for a mid-4, as that one was at depth. Vanuatu, a 5.0. So not that much activity there. Let's move on to some other data. Head to spaceweathernews.com. X-ray flux, nothing to comment on. BTBZ is very convergent on the 0 line right now. No phi angle signal. Solar wind density down to about 3 protons per cubic centimeter, with a slight increase in solar wind speed here. Looks like the wind speed is up to about 400 kilometers per second. So that's a standard signature of a coronal hole wind speed, wind stream. KP has dropped back down to 2. Would not be surprised to see that go back up. And we got some interesting spikes in the magnetometer data there, as you can see. We will look at the geospace in a moment. And there's your electron flux dip, consistent with coronal hole wind streams. Ionosphere not particularly charged. There's your F2 ionosphere layer. And let's talk about the F2 ionosphere layer for a second, as we got a question from a viewer yesterday regarding the F2 ionosphere layer. Now, first of all, let's stay on this map for a second. The sun is going to be right around this area in front of this blob, because this charging part kind of follows the sun throughout the day, first of all. So, in other words, you can look at this map and tell where the sun is most of the time just by seeing where the most highly charged section is. Now, this map is extremely discharged right now. It's only down at 8 megahertz. It doesn't get much lower than this. So the incoming solar radiation is actually quite weak. And part of the reason we look at this is because it gives us an idea. There are a lot of proportional things going on here. You've got incoming protons, you've got electrons that are in the ionosphere, you've got other ionized particles and solar protons, molecular hydrogen, hydrogen nuclei, helium nuclei, molecular helium, and a little bit of all of the atoms on the whole planet. Now let's look at some other stuff here. To really understand the ionosphere, you need to understand the solar wind, because the solar wind is the progenitor to the ionosphere. So you got the solar wind, it comes in like this, and then it's going to split into field-aligned currents. These are the Birkeland currents that come into the Earth at the poles and eventually cause the aurora borealis and aurora australis. Now, this diagram, pretty much the whole thing is the Earth's magnetosphere. But the ionosphere is just the most upper layer of the atmosphere, way down in here, underneath the Van Allen belts. And then, of course, so in any case, to tie this to the map we were looking at, when you're looking at that flattened map, the side with the charged up blob is this side of the planet, and the discharged side is this side of the planet. That's the way it works every day. And now let's look at some extra diagrams here. Also, just a consumer tip, when you're watching, so here's a map of the Earth's atmosphere. You can see troposphere goes up to about 15 kilometers. Stratosphere to about 50 kilometers. And so on. You can see the different layers there. And we measure the electron flux at the F2 layer because that's the maximum electron density. That's the most energetic portion of the, the thermosphere there. Now the ionosphere, it does shrink and grow with daytime, nighttime transitions. Let's take a look at that real quick. Here's just another more simple layer, more simple image of ionospheric layers. Troposphere is where all the weather occurs. And so on. Just another diagram there showing you that the ionosphere sometimes gets pressed down into the stratosphere and so on. And we name the layers D, E, and F based on their proximity to the planet. Here's another diagram of the way radio propagation differs between daytime and nighttime. And the reason for that is because the F2 layer goes away. At nighttime, we have no F1 and F2 layer. We only have an F layer of the ionosphere. And that is because of the charge-discharge feature. When the sun's out, charging with positive. When the sun's not out, discharging negative. Anyway, we hope that helped the understanding of the F2 ionosphere layer. The reason that we look at this is because this is kind of the direct fingerprint from the sun. You can't look up and see a cloud being affected by the sun directly, particularly, or anything like that. So we look at the F2 ionosphere layer because this is telling us the direct effect on the ionosphere. Solar forcing runs the world. Now, since we got some odd magnetic perturbations on the GOES magnetometer, let's take a look at that. First, North America. There's your magnetic perturbations over North America. Notice there was a little bit of anomalous looking stuff that seems to be kind of centered on Alaska right now. Let that play through one more time. Not super powerful, but a little bit anomalous there. You can see it stretching all the way down to the Pacific Ocean. And let's look at it over the globe. Let that play through. That northern perturbation went all the way down to Hawaii. And last but not least, let's look at the polar view. By the way, we will leave links to all the images and websites that we use as we do daily. Let that play through. Some interesting magnetic anomalies coming out of there. Probably not caused by the sun, caused by the Earth's magnetic field, or, well, lack thereof. And let's do a value-added service here and look at some weather stuff before we get into some nonsensical weeds. Looking at the U.S. Doppler radar early in the morning on AccuWeather.com, so you might not have to, because you follow space weather. And since Earth weather is caused by space weather, we just cover both. And let's look at the water vapor map so you can see what's going on in the upper level. So as you can see there, you've got massive amount of dry, high-pressure air pushing through the east. Kicking up a little bit of snow in the main area. Atmospheric river is starting to make its turn to the east and the northwest there. It's starting to head over this way. Got a cyclonic convergence zone near the New Mexico border. Strong winds on the east coast. Now let's show you your jet stream by looking at the 250 millibar wind speed. Your global jet stream. Let it play through. This includes the forecast up to, I think, the 26th. It'll have a timestamp. There's your meridional jet stream flow. All over the map. Southern jet stream looks super weak. I mean, this area here looks completely anomalous. Some strange low pressure areas kind of floating around Alaska. And this insane loop that comes out of the jet stream right here. Check that out. It's bizarre. Anyway, that forecast is actually through the rest of the year. January 2nd, January 3rd. Yeah. 2 weeks. And we'll leave links to that also. And let's go to a ridiculous article on phys.org. Oh, the full story on climate change requires the long view. They're not going to give you the long view. What they're going to do is they're going to try to blame different regions of the world for their emissions. Something to do with their carbon footprint obligations, or some nonsensical BS crap not based on any science. Radiative forcing is not real. The greenhouse gas on our planet is water. And, you know, we'll leave links to the article. I couldn't get through the whole thing because it was so stupid and idiotic. So let's... Oh, wait. The full story... Let's just take their headline and just expound on that a little bit. The full story on climate change requires the long view. First of all, you hack frauds, Here's the global temperature average versus atmospheric CO2 over the last 590, 600 million years. Really, it's only like 550 million years, but boy, isn't it strange how we had really high CO2 here and really low temperatures? It almost seems like they're not correlated. Because they're not correlated. Let's look at another image. How about the last 415,000 years of temperature change? This is part of 2 Milankovitch cycles here. Actually, it's part of 3 Milankovitch cycles. This is the normal temperature of the planet. Much cooler than it currently is. And these are the tiny little interglacial periods. You see that? All of human history, all of recorded human history, takes place right there. That's it. And now, last but not least, let's look at the temperature curve for the last 15,000 years. All right? Here's the Minoan warm period. Here's the Roman warm period. Here's the medieval warm period. And here's the current global warming. Okay? Antarctica formed when the planet was 3 degrees warmer than it is right now, about 33 million years ago. And here's... Wait, can we see that? Yeah. Oh my gosh. The planet's burning up. And before we close things out, indoor tomato update. There you go. There's a penny for scale. It's coming along pretty nicely. And we would close things out in the 193 angstroms view, but it's not really loading. So let's just stick to this. Thanks, subscribers. Please don't forget to like and subscribe the videos and channel. If you enjoy the content, help us get to 1,000 subscribers. Questions and comments are welcome. We are taking suggestions as to what we should do for our 1,000 subscribers special. Remember, if you're driving, don't drink. And if you drink, don't drive. And if you drive, don't drive. Just don't drive. Because then you'll be on the road, and I might be on the road, and I don't want you there.